Hi everyone, today we have Ben Caldwell tell us about the VyZX, formal verification of a graphical language, and the floor is yours.
Right. Yeah, thank you. So like she said, I'm going to be talking about this project we've been working on where we're trying to verify properties of ZX calculus embedded inside of another proof assistant. Um, Whenever you talk about verifying, sort of the immediate question arises of why are you doing this? And there's a couple of reasons to verify things. Sometimes, particularly mathematicians will like to use it just to double check their reasoning. Um, that's not really what we're doing here, although if you wanted to do that, there are a couple of tools out there that exist. There's Quantumatic, Chip, both have different takes on this. How do you actually go about assisting reasoning in these diagrammatic languages? Um, and you can really do this with just axioms and build a tool specifically for this. And that's oftentimes what mathematicians will do. Instead, we want to embed it in a proof system without axiomatizing anything. We hope to get a couple of benefits from this. The first one is we're going to embed it in another proof assistant, so we get to use some of the tools of that proof assistant. Typically, this means code extraction. So you're able to take verified code and convert it into another language. Um, in our case, we're using Coq, which has extraction to languages like OCaml and Haskell. And then we also get to interact with the libraries that already exist embedded in this proof system. One of which is Squire, another which is QuantumLib. Squire stands for Small Quantum Intermediate Representation. It's built on top of QuantumLib, which is a matrix library, and allows us to reason about about quantum gates. So that's really what we're looking to do here. We want to embed this language in Coq, utilize the tools of this proof assistant, and interact with the other things in this environment. So it's not just about assisting reasoning, although in practice you can use this to assist your reasoning. It's more about verifying code. Um, so in our approach, in order to avoid axiomatizing things, we have to have some sort of semantic backing. We have to find some way to evaluate diagrams as matrices. Um, this is compelling to us as proof engineers, and ultimately this is what's called a proof engineering project, because it gives us a smaller core of truth. There's less things we have to trust, right? If we're doing this semantic evaluation versus axiomatizing everything. If we axiomatize things and we got an axiom wrong, then suddenly we've kind of broken our whole system. Um, This also enables us to have verified conversions between circuits and diagrams, right? Because our circuits also have a semantic backing and our diagrams have a semantic backing. We can say, okay, well, translate circuits to diagrams. And as long as the semantics are equal, then we know that's a verified translation. And it's fairly easy to state diagram equivalence using these semantics. There is, however, a cost. It's difficult to apply these semantics to the ZX calculus because they can be undirected and potentially have cycles. Typically, it's fairly easy to apply semantics to something that's acyclic, like a tree. But when you have these potentially cyclic undirected graphs, it can be a bit more troublesome. However, if you just as we kind of went through the literature of the ZX calculus and even this image, which we just took from the ZX calculus website tutorial, there's this kind of idea that if you want to compute the semantics for your diagram, you could break it down into these pieces where every cell has exactly one element, and then you know the semantics of each of those elements, and so this gives you an easy way to compute them. And so we can kind of look at what these elements have to be. You have caps and cups, swaps, composition of diagrams, parallel diagrams, single wires, and then the generators. And so I've enclosed these because things on the outside exist for generic string diagrams, and the things inside the box exist specifically for the ZX calculus. There's other ways to arrive to this. You can get here through the language of category theory and look at how these categories are constructed and then translate those definitions into an inductive constructor within our proof assistant. But looking at it from this sort of how do we practically compute semantics can inspire us to get a nice simple representation. Um, So we'll take these constructs and we'll build some inductive constructors, and these constructors will be given sort of with the generators saying, okay, well, I have to know how many wires are going in, how many wires are going out on the left and right, and what the rotation of my spiders are, and then I can make spiders of either kind. I have to be able to say I can create caps, cups, swaps, and I do have to have the empty diagram. Um, and then I should be able to compose diagrams where the dimensions here, so ZX1 and ZX2 on this composition, the middle dimension agrees. So we're enforcing that at the type level. We're adding in wires and we're adding in boxes. And then we're able to stack diagrams sort of arbitrarily. The dimensions don't really matter here. Just the result has to be a sum. And then we actually apply the semantic in exactly the way you might expect, where we just build this large matrix where most things are zeros, except the top left corner and the bottom right. They're 1 and e to the I alpha. And to do the X spider, we found it was easier just to compose a bunch of Hadamards on either side. And yeah, so cap, cup, swap, empty, all things you might expect, wire, the box just resulting in the Hadamard. Composition here flips the order. These should not say semantics. It should be just the double brackets. We swap the order for composition, and we use the Kronecker product for our stacks. And then we can use this semantic function to just define our proportionality. Things are proportional if there's a non-zero scalar multiple such that their semantics are equal. And when we encode this, we then can use this to actually talk about performing rewrites on our diagrams. When we actually do a proof in Coq, we sort of have three significant portions. We have tactics, we have our hypotheses, and we have our goals. Our goals are what we're trying to prove. Our hypotheses are what we know. And the tactics are how we update our goals or our hypotheses step by step. Overall, we'll call this our proof state, right? And a proof in Coq, you got to start them like this, where you have to say, oh, well, it's some lemma, you name it, and then you make the statement. This is just commutation of addition. Each of the red lines here constitutes a tactic. Each of these n and m's called in here are either hypotheses in the case of n and m here, or in the case of nat add 0r. This is a theorem that was proven previously. And when we're actually practically doing proof, we sort of have our goals and our hypotheses side by side over here. And they're rendered based on what our currently active line is. So this is what we have our inductive representation of the ZX diagrams. This is what it looks like when we're actually doing these proofs. It ends up being a little difficult to follow sometimes, especially when you're dealing with larger diagrams. So we have an extension that'll work with the language server and actually renders the diagrams for us. In the second half, I'm going to be taking a look at how do we actually, a couple of examples of how we do proof. And so we'll get to see what that looks like. But in general, the way we've chosen to render things is if you have two diagrams, a z-spider will be rendered as this green block with inputs on the left, outputs on the right, and rotations in the middle. When things are composed together, we put this border around here, and this is sort of one immediate flaw of doing this embedding, is compose and stack and all these things, they have associativity information in them when we do this inside of a proof assistant. But oftentimes when you're dealing with diagrams, you don't think about this, right? There's ways to get around this that we can discuss later, but in practice right now, in the state we have, you kind of have to work with this associativity information kind of closely. And so when we're actually rendering a diagram, this is what it'll kind of look like. You'll have the inductive representation up here, but then you have the diagrammatic. And so you see these two on the left here have this dash border, which means they're stacked together and it's more closely associated than the compose with the thing on the right. So this is just saying that essentially we can fuse these two into here and add their rotations all together. So I talked about using tactics to rewrite our goals. And then practically what this means is if we have some sort of equality, we can use a tactic rewrite. So this equality here is P. P is just a statement that G is equal to H. And our goal initially in this proof was G. When we do rewrite P, it replaces every G with H. And that's exactly what we would like to have happen with our proportionality relation. We don't get this for free. We had to put in a bit of work using tools within Calc that are called parametric relations and parametric morphisms. The parametric relation just says that proportionality is reflexive, symmetric, and transitive, while the parametric morphism tells us how the proportionality interacts with things like stack and compose. Essentially, it gives us the ability to rewrite within diagrams within Calc, which is something that's really compelling and something we'd really like to have happen. And we have to go to this level of saying, essentially convincing the proof assistant that, yeah, okay, if you have a statement of proportionality between two things, and then you stack or compose things around those two things, the proportionality relation still works. And yeah, the other tactic is sort of apply. Apply works in a similar way. We had some goal G. We could here do apply of this hypothesis to update this G to H, and then we could provide this little H to actually prove this statement. So in VyZX, we have three proof strategies, which we've kind of identified at this point. The first of which being a proof through semantics, where we actually have to sort of get our hands dirty, look at what the semantics of the diagram is, and do the proof by hand. We have inductive proof, which is a bit more diagrammatic than just proof through semantics. But we still typically have to handle some base case computationally. And then we have strictly diagrammatic proof. And this is sort of the end goal for VyZX. We want everything to really be done through diagrammatic proof. In practice right now, we have a complete rule set for the VyZX calculus implemented. But in practice, there are times where you'd want to go down to do a proof by semantics. Maybe it's easier for the statement you're trying to prove, or some other similar situation. And yeah, so this is the part where I say that I'm going to be doing a bit of live coding where we step through some examples of these different kinds of proof. Are you all able to see this?
Oh,
Yes,
good.
we can see it.
Okay. So first thing I'm going to do is I'm going to turn on the visualization. And I'm going to get this set up. So this will kind of translate these statements into these diagrams. And feel free to interrupt me at any time during this process because these proofs can go fairly quickly, but they may be somewhat unfamiliar. So, right, if we want to prove a simple statement like identity removal, we kind of have to go down to the semantics. We don't have much of a choice. And we have this one statement, prop exists non-zero, which now the rendering is not going to be relevant anymore. But prop exists non-zero takes us from a statement about proportionality and turns us into a statement about equality. And then we have this semantic equivalence, which will take us to Dirac notation once we unfold it. So we can unfold our Z spider into the Dirac form that you can see here. We can get rid of the C1, and then essentially this is just solve matrix down here just computes the result. So a lot of simple goals can be solved this way, where you just turn into the semantics and then you throw a computational solver at it. And now anywhere if we run into this pattern, we can replace it with a wire. Sometimes our computational proofs do get a bit harder. Right, we have this statement here where any spiders that have exactly one connection to them can be fused together. We can kind of start it in the same way, where we take ourselves to the Dirac notation. And then we have to really closely associate these things. So we'll get everything, multiplied and distributed over the addition. So now we have sort of these 4 statements. This one here, this one here, this one here, and this final statement. We'll get the scalars moved out too. And now essentially what we have to do is target this part. So what we're going to do is target this part by getting this 0 Bra-Enquete pair closely associated. This 1 and 0, this 0 and 1, and this 1 and 1 closely associated together. We can do that in one line like this. Now that they're closely associated, we can do computation on them. We know this should be an identity 1. This should be a 0 matrix, and an identity 1. And we have a database which lets you do these all automatically. And now we need to simplify things. A lot of this stuff, when we're dealing with proof at this level, we want it to be vastly automated. You don't want to be having to do like by hand, tell it, oh, well, that's a 0, so it'll multiply, that multiplication will become a 0. In practice, we have this thing down here called msimple, which will handle all of that for us. So msimple will essentially say, okay, well, there's 0 multiplied by things here, so that should just disappear. And then 1 multiplied by I1 multiplied by things, so that should just disappear. And we're left with the statement that's almost what we need, right? The first side of the addition is good, but the second side is the scalars need to be moved around. And we can handle that all automatically with these auto rewrite tactics. And then that solves our slightly more complicated computational proof. And in practice, this is
Sorry,
sort of,
can I ask about this?
yeah, absolutely.
Because this is any number of inputs, right? You have this
Yes.
notation for like number of inputs, tensor, and then some value.
Yeah. So this notation right here, is that what you're referring to?
Yeah.
Yeah, so that's just the Kronecker product repeated n times. Yeah, it's exactly what you might expect. Yeah.
Right, and so you're sort of telling it that like it should unroll the output, but not this part as a matrix.
Yeah.
Okay. Yeah. Clear. Thanks.
Yeah, and feel free to interrupt anyone during all this. I know this is not the usual ZX fare.
So may I ask, when you look at the ZX diagram, you just read it from left to right and identify a horizontal component whenever you reach like spiders?
So in this diagram down here, or
like a more complicated one where you have many spiders, many connectivities, many horizontal component.
Yeah, so it can get a little tricky, and I think the third example is going to be it's going to have a couple of those, so we will get to sort of how that looks.
Okay.
But yeah, you end up getting, in those contexts, you end up getting a lot of these associativity information, dashed lines, and it does get increasingly more complex.
And the way that you comprehend it or the way you parse it is not unique, right?
Yes. So a single diagram can have multiple different equivalent representations with this block structure.
Okay, thank you.
Yeah, and that's sort of why we have to deal with all this associativity information, because we don't have this guarantee of uniqueness. There is work we're doing to kind of get to that point, but as it stands in the tool right now, we aren't there yet, but we found that we don't need to get there in order to give complete rewrite system for the ZX calculus. Okay, so the second kind of proof that I mentioned was inductive, and this is sort of a blend between diagrammatic and computational. We tend to find we have to do computation on a small, potentially finite diagram. and that we can use that to then talk about diagrams that have a parameter we're operating over. So in this statement, the parameter we're looking at is M in the center here. We want to show that any diagrams that at least have one connection, as long as they're only connected to each other, we can fuse those together. And so we're going to do this by looking at induction on the argument M, which is the middle dimension here. What induction does is it gives us two different proof goals. The first one, it substitutes M for 0, and because it was the successor of M, that ends up being 1. And we can just apply our rule that we just showed computationally. And in the second case, it looks at the successor of M, and then it says, okay, well, this statement is true for the predecessor case. So for S of M, it's true, and now show it for S of M. And this is where we start to get a bit more complicated diagrams. So at the start here, we're calling on these two lemmas, grow Z top right and grow Z top left. Grow Z top right essentially splits this 1, 2 spider out over here, and top left splits this 2, 1 spider out over here. And then we can, reassociate the composition. So now instead of this block and this block being separate, this is now associated to the right fully. And then we want to reassociate the stuff in the middle so it's close together. And now, so these two are almost touching. However, this stack here and this stack here are kind of getting in the way. We can redistribute the stack and compose relative to each other as long as the dimensions work out. In this case, they do, because it's just 1, 2, 2, 1, and M. So now these two are closely associated, and this is where we bring in another computationally proven rule that if we have a 1, 2, 1, a 1, 2 spider and a 2, 1 spider, we can fuse them together. We could have done strong induction and kind of gotten this for free as well. But when we're just doing simple induction, we often find we have to do these small little computational tricks. Right, and now we can take this 0 plus 0 and turn it into just a 0. And this is the part where we're finally able to use some automation tricks. We have this automation cleanup ZX. And what this is going to do is going to say, okay, well, this 1, 0, 1 here is a wire. And these are just wires composed with each other. So we can get rid of all of this stuff in the middle. And we're left with this statement, which looks like where we started, except there's 1 less plus 1 here. Right, we've shrunk down the dimension, and in fact, it matches the diagram that you would get for that's not working. The copying here is a little finicky sometimes. Okay, it looks exactly like the statement of the inductive hypothesis. So we're actually able to just use the inductive hypothesis. We can call apply, and then we're done. We've proven the statement. And so sometimes we have to straddle the line between these semantic proofs and these diagrammatic reasoning, right? For this second part here, we do diagrammatic reasoning in order to reassociate things and fuse some things together. But to get there, we had to do a couple of computational base cases. In particular, this 1-1 fusion and this 1-2-1 fusion. But some proof we're able to just kind of look at this at just the diagrammatic level. We can take and define this Bell state prep, and I'll unfold it very quickly so we can see what it looks like. Essentially, this is the normal Bell state prep circuit, right? Where you have 2 0 states, you do a Hadamard and then a C0. The C0s have to look like this. This is sort of a restriction, right, of how we've defined things. There's no straight up and down wire, like you like to do in the ZX calculus when you know that it doesn't matter which side it's on. Here we kind of had to enforce, well, the green spider comes first and then the red spider comes second. We can show that it's equivalent to moving it and swapping the sides of these two things, but it is a restriction of how things have been defined here. And then, yeah, this is mostly going to be a lot of reassociating. First thing we're going to do, though, is take a look at this left side. We have this pattern where we have two things stacked, and we really want to have this X spider and this Hadamard together so we can swap the colors. So we can do stack, compose, distribute, and then we can look at this sublemma here where we just say, okay, I just want to show this real quick. And we'll do this replace here. This symbol here, this circle with the dot in it, is a function that we've defined over diagrams, which just swaps the color of them. And so we're replacing this with the color swap because this is how the color swap would evaluate. So it's a very quick statement to do. And then we know how this color swapping function relates to diagrammatic properties. So we can say, okay, well, that's a color swap of something. So just put Hadamards all around it. And then we'll simplify and clean up. And this, so initially how this kind of looks is it has 0 Hadamards pushed over here because there's 0 inputs and 1 stacked over here. But using some of the automation we have to clean things up, you can very easily deal with these statements. So you get it to sort of the state that you'd expect it to be in. We can associate these Hadamards together, and cleaning up the diagram with cleanup ZX knows 2 Hadamards cancel, so we can prove the statement. Now these are exactly equivalent, so we can just say, oh, well, it's easy. And then we can use that statement immediately after proving it to swap the color of this. And cleaning up the ZX diagram, we'll get rid of this wire down here. Okay, so yeah, next thing we want to do is probably fuse these things together as much as we can, right? So we will reassociate our compose, do the same stack trick to get these things just so they're touching. And then we can actually get rid of the wire, fuse the Z spiders together. And now things get a little tricky. Because this has 2 outputs and this has 1, we can't do that same stack, compose, distribute trick before, because the dimensions in the middle don't line up. So what we need to do is we need to push this green 0-2 spider out and try to look at just this side where we have just these wires we've kind of moved. We'll reassociate things, so now we've got these wires closer, and we can split this wire stack up into 2 individual wires. And now we need this 2 to have a stack where there's 2 on the bottom down here, so we can reassociate things. Now the dimensions of these stacks do line up, right? We have 2 outputs here, 2 inputs here, 1 output here, 1 input here. So we can do that compose distribute trick again. This is it's sort of a headache when you have to do these things. I'll talk in a bit about, there are ways that we can think about getting around this. They just aren't implemented yet. And now we have some lemma that we've shown previously that says, okay, well, there's a spider that's strictly smaller in dimension than another that is connected to. We call that dominated spider fusion. And so we're able to fuse these things together. And now it's just a bunch of cleanups, right? We're cleaning up, getting rid of these wires. This 0 stack of wires here just disappears. And we're left with a bunch of things that we should be able to convert into wires, right? So this is a X spider, one input, 1 output, no rotation. We can change that into a wire, bundle up our wires and clean things up. And then we know that a 0 input, 2 output spider with no rotation is a cap. And we've proven this. During the process of doing some of these proofs, you'll generate some goals over time that deal with how the dimensions, equalities among dimensions. Typically, these are all solvable in sort of just one go.
So what does it mean to have a goal that show up?
So, oh yeah. So these goals, this is sort of a finicky thing. We have the ability to cast diagrams from one dimension. So the inputs and outputs are their dimension. From one set of inputs and outputs to another, as long as they're equivalent. This could be like if you have a diagram where the dimension is x plus and then in parentheses y plus z, you can cast that to a diagram that's x plus y in parentheses and then plus z. So you can reassociate these things. And oftentimes we find these generate goals when we're getting rid of them. It's another restriction of how compose works because the middle of the compose has to agree exactly. We often have to use these casts for that. There's a single piece of automation. Yes, simple casts. This right here is what generates these goals. And essentially it's doing the work of saying, yeah, I can make these dimensions agree. And I can get rid of any of these casts that you've had to put in order to convince the proof assistant that dimensions agree. And so a goal that generates is then just saying, okay, you actually do have to still convince the proof assistant that you can show these equalities hold. And you'll see right here, these equalities are just associativity, essentially. It comes up with stack a lot. It's one of the things that we often have to deal with. But they're all solvable very quickly, especially in finite cases like this. And so does that answer your question?
So a goal is something that needs to be proven. So saying, oh, given that this is true, I can prove it.
Yes.
Okay. Yeah. Okay.
Yeah. Yeah. Goals are simply just what we need to prove. And yeah, so this proof, we were able to do this without actually reaching down into the semantics, which is fairly satisfying. And really sort of the end goal for VyZX is we want to be able to do this in any context. There are a couple of steps to get there, but what we currently have is the ability to, we have a complete set of rewrite rules, which we've proven in Calc. We have automation to simplify diagrams, which comes up a lot, and I've had to use it in quite a few of these proofs. I've forgotten what reasoning about should be there. I think that is reasoning about arbitrary diagrams. So we should be able to construct any ZX diagram and reason about it using this sort of inductive construct. There are flaws to this, right? Some of those have been pointed out already. There's multiple ways to encode any individual diagram, and we have to deal with this associativity information because of it. And even though, we have a complete set of rules, you still do have to do proof with semantics occasionally. And there's issues with dimension. But what we really hope for, and one of the things that we've done is we were doing this as an exploration, not just of the VyZX calculus in specific, but these categorical string diagrams. And so we have some work that we split off into its own project called Vicar. And it includes proofs that VyZX itself satisfies the definition of Dagger compact categories. But it's also supposed to be a generic framework from which you can show something is a category and get some sort of string diagram visualization in this style. Going into the future, we're trying to find a way to actually deal with connection information, because in practice, if you're talking about wanting to write an optimizer or anything on top of this, depending on the optimization you're trying to do, it might not be great in this block structure. There are potentially optimizations that we think work pretty well in this block structure, but certainly we don't expect all of them to work well. The more strictly graph theoretic ones, we don't think, at least I don't think, will be ideal in this. So giving us the ability to say, define a graph as an adjacency list or a similar operator and turn them into this block structure to give it semantics kind of solves the initial problem we had when we were trying to deal with these graphs where we had a lot of trouble actually giving a semantic to it. But we think that translating into this block structure will make things a little easier. We want to use this to then maybe verify as an ZX-based compiler. There's some work on on verified optimization of quantum circuits called VOX, which we think we could integrate well with. And really, we want to be able to not worry about associativity information when we're actually dealing with diagrammatic rewrites. One of the paths to that is, having the adjacency information decode into the block structure and then just worry about the adjacency information. But there's a lot of work that's been done, particularly in Coq, on rewriting modulo associativity and commutativity. If we could extend that with some of the extra rules that we have here, then we think that's a really promising system. We've seen work on e-graphs, which can kind of be applicable here. And we're hoping to sort of integrate that going into the future. In fact, we already have the ability to take an adjacency list like representation and turn them into block diagrams. Our next step with that is kind of just exploring how that actually behaves and how we can state these rules in a proof assistant at that level. Yeah, so thank you very much for your attention. In summary, we've looked at defining these ZX diagrams inductively, sort of inspired by string diagrams. And there's a lot of category theory you can go back into to also look for reasonable inspiration for this. So anywhere you have a categorical backing of your field, we believe that this should be applicable. We've run into other people who are doing similar things right around now. And we looked at how these proof strategies actually kind of behave in practice. We're on GitHub. The paper is on the archive. And I have some references here. This second reference, inductive diagrams for causal reasoning, is a similar work to what we've done here, but it's for reasoning about parallelism. And we somehow, at the same time, came to a very similar construct as them, so it's somewhat interesting. Yeah, thank you.
All right, thanks, Ben. Thank you for the talk. Sorry, I missed the first part, so I was late from another meeting. Do you have any questions from the audience? Otherwise, I have some.
I have a question.
Okay.
Thank you very much for the talk. I wonder, just now you talk about like those lemmas, like when you do the demo, are those the proof strategy that you mentioned at the end? Like, for example, you locally identify the Bell state prep block, and then you discuss how to simplify it.
Right, yeah. So that is, these are, when you say the proof strategy, you mean these three, right?
I meant just now when you try to prove the lemma, for example, Bell state prep, you have this step-by-step rewrite of your diagrams. And I wonder if this lemma is like a local optimizer or like that kind of simplify your diagram locally.
Yeah, it exactly is. So what we could do is write some paths that looks at diagrams and find some diagram that is equivalent to this up to associativity and commutativity. And then what the optimizer would do is locally it would replace it with a Bell state. And then what this lemma lets us do is prove that optimization is correct. So yeah, these are sort of like people optimizations, right? We're looking at something very local and saying we can do this. But there's no sort of optimization passes built yet.
Yeah, I was curious. So let's say someone give you a ZX diagram, and there are different ways for you to apply different people optimizer. Then how do you know which order do you apply them? Because maybe some order will give you a very short proof, some order will give you a long proof, and maybe sometimes the proof is so long that it just cannot terminate in a reasonable amount of time. How do you know at that point if it's just the ZX diagram do not match, or just because you have not complete the verification yet?
Yeah, so in practice, I have seen a couple of proofs that just kind of extend and extend, and it doesn't seem to be getting better. Particularly when I've had to do proof by semantic purely. That's something that I've experienced. And as for when we can tell it's the proof versus the diagram, I don't think I have a great answer for that. Sort of in practice, we've just thrown our heads at this and just tried to, crunch it down over time. And sometimes we have to step back and restart. But yeah, it's very possible that like when we're in a proof, we can kind of get lost in the weeds. I have some proofs that go on for hundreds of lines. And the difficulty in verification, and in particularly in a proof engineering project like this, isn't so much in the ideas that you're trying to communicate, but the work that it takes to get there and to convince the proof assistant.
Is it possible to find out statistically which local optimizer is more likely to be useful? So you always prioritize that whenever you have different options, like to apply this people lemmas.
I would imagine that there's some way to figure out the optimal, although I'm not, I think I'm not well versed enough in any statistical techniques to say. It's an interesting point. It does seem like there should be some way to figure out what's optimal to do. There are some normalization results, if I'm not mistaken, right?
I mean, there are general normal forms, but they're exponentially large. So then, like, you can do it, but it just takes a lot of time.
Mm-hmm. Okay, so then finding out how to do it without it taking forever. Yeah, okay, there is sort of one thing that we're trying to look at, although I don't know if it can really handle the exponential growth. It's supposed to try. There's this Popple paper in 2021 called eGraphs Good, which deals with a lot of these rewrites and finding out the optimal, or it was called eGraphs Good, which tries to deal with a lot of these rewrite rules. It's something we've been thinking about trying to wrap into our project. Although I don't know if it'll solve the exponential growth issue. It's definitely something worth exploring, and I think it's very interesting.
Is it this one I put in the chat?
Let me see. That's the GitHub, yeah.
Oh, okay, thank you.
Yeah, it's a very interesting paper. They have a YouTube talk from Popple, and it got distinguished paper. Yeah, you can see the link to that on the website here.
Mm-hmm.
Yeah, it's a really interesting paper and something that might be relevant to the question you've asked, although it's just not something I'm familiar enough to say.
So, question.
Yeah.
So in terms of this formal proofing, to me, it seems like some layers of it are akin to sort of doing it by hand, where you apply diagrammatic rewrites. All the parts are like all the stuff around associativity is very much sort of seems like boilerplate that's around it, right?
Exactly. Yeah.
And so then it feels like there would be two ways to do all this. One would be like a proof assistant that naturally understands rewriting modular associativity, and you sort of refer to this existing in COP.
Yeah, so there's some work built on top of egg and some work not built on top of egg that deals with rewriting modulo associativity commutativity. It's not far enough for what we need, so we would have to extend this work, but yeah, these things exist.
But then the other way would also be that, because it seems quite machine-like, right? The kind of associativity steps you have to do. So you could imagine like a software program outside of COP that sort of, I give you these two diagrams and like the associativity structure, and then it gives me the path of associativity rewrites I have to do to make it work.
Mm-hmm.
And then I just insert those lines, just generate some lines in COP that you have to run, and then push those in COP.
Yeah.
Is something like that, is that reasonable that you would do something like that instead, or?
Yeah, that's actually the goal that we have using egg. So I'm not an expert on this. This is more Adrian's work on this, but as I understand it, somebody for a bachelor's thesis implemented a plugin using egg that does essentially what you just described, where you can hand it some rewrite rule and then it'll say, okay, well, I know from this rewrite rule what I need to have show up. And I know I have these associativity, commutativity rewrite rules. We have this, in this context, we have this distributivity thing too, which is very important. And it'll try to get there, and then part of the magic of it, as I understand, is it cuts a short path. But it can like grow exponentially and have all these different rewrite rules that it's considering doing and all these different paths. They put in a lot of work on egg to try and reduce that size, which is why that's the program that we're looking at to do this job.
Is the calculating the right associativity path, is that a computable program? Is that sort of like is it solvable in principle even, or is it only heuristic?
I'm not sure. Yeah, I would believe it's solvable in principle, or at least getting good enough is solvable in principle. But again, it's not something I'm personally super familiar with. So this is all speculation and intuition.
Yeah, so I guess like the thing I'm asking this for is I don't know if you're familiar with ZX Live, which is
I'm not.
we are intending this to be a sort of a graphical proof assistant for ZX, but then like not in a formalized manner, but just a GUI where you have some diagrams and you can apply some local rewrites, and the structure is just as a graph, right? Like it doesn't have to do with associativity stuff.
So
and it's not formalized, it's just like some Python script and stuff.
Sort of like quantumatic.
Yeah, it's like quantumatic, but a bit simpler, more easy to use, less general than quantumatic, essentially, like more specific to ZX. It would be nice if you could sort of make a sort of intuitive proof there, and then you sort of click like export to VyZX or export to Coq, and then it creates like a formal path. And I think that the missing ingredient there would be figuring out these associativity conditions. Does that sound about?
That sounds, that sounds amazing, honestly. And it does seem like the missing ingredient there is the associativity, commutativity, distributivity stuff. Because really, with the inductive structure we have here, that's all that differs from a standard ZX diagram.
All right, nice. Anyone else? Any questions, remarks from the audience? Okay, then
actually, I have questions. Yeah, I was worried about other people want to ask questions. So I wonder, just now you said about using this could find underlying categorical structure. I didn't get a connection between using VyZX and looking at the categorical structure of like stuff. So could you give an example?
Yeah, so right, if you let me see if it's in this branch or not. I don't think it is. Let me see if I can open Vicar, or if it's, no, I don't have it here. Okay. Yeah, so sort of what I mean by that is a couple of these constructors here are derived exactly from the definitions of a category. Cap and cup come from, I believe, rigid categories. Empty and stack come from monoidal categories. Wires, just something that has to show up in category by itself. Swap has to come from a symmetric category, or if you were dealing with a braided category, you might have a braid there. And so when I say identify the categorical structure, that's really what I mean. Like if you wanted to do something like this similar for knot theory, right, you would be looking at a braided monoidal category. And so the constructors that you define for that would have to differ from the constructors you define for this. But in principle, it seems like these things should be the same in practice. If you're dealing with like a Cartesian closed category, you might have to have the copy operator. You might have to throw other things in. So really, yeah, it's more identifying what categorical definitions correspond to whatever you're trying to do. That's really what I mean when I say identify the categorical structure.
The other thing is, have you tested the scalability of this verification? Like, up to what point that you could see that your program runs really, really slow and it's no longer reasonable to get an answer?
Yeah, so in practice, we've done some work on larger diagrams, but nothing beyond like 18 spiders. You know, we haven't done anything very large. But at least for us, when we're dealing with it purely diagrammatically, we don't find it has a lot of slowdown. If you took the diagram and you tried to unfold it to semantics and you have 16 or 18 spiders, I have noticed that it slows down. And in practice, the way we have to deal with those is sort of go after them piecemeal. This was something that we had to do for getting a complete set of rewrite rules. I believe the rules that we implemented were the non-C rules, which can have some slightly larger diagrams than the Oxford rules. And so in practice, to verify some of those correct, we had to break down our semantics quite a lot.
And if, oh, sorry, you go first. Do you still want to show something?
No, I was just going to see if I had the completeness result. Yeah. So these proofs, I just wanted to show how horrible these can really get. This is one proof. It goes on for 400 or so lines. It took quite a bit to figure out the right way to do this, but the trick ended up being breaking down large diagrams into smaller pieces. And yeah, this is probably the largest proof that we've done. And it works fine at the diagrammatic level, but at the semantic level, things did start to break down. And as you can see, this is really hard to track where the connections actually are, right? We're hoping as we deal with diagrams that are like adjacency lists, we'll be able to, and deal with modulo associativity, commutativity, we'll be able to make a better rendering. Because if you could do rewrites without caring about associativity or commutativity, then your rendering doesn't have to care about it. And so you could just render a typical ZX diagram.